All right. Well, okay, no one's here, but this is good practice for me to pretend like I'm talking to an unfamiliar audience. So I'll just recap what I'm doing here. I've made many logic gates out of Nand gates, and each time I created a gate, I was able to use it downstream. So for example, this one's a not, and this one's an and then later on I can use the and like I'm using here. So I'm going to implement these in the hardware simulator on the Nand2Tetris website, and so why am I doing this? I've always wanted to know how a computer works, and this is the book. This is the book to learn how a computer works. So that's what we're doing. All right. All right, let's go. Here we go. So okay, so there's one in, one out. So yeah, that's nice. They have autocomplete. Equals in, B equals in, and out equals out. Okay, so how do the last time I tried this, I was using the Java app. So let's see. Okay, so we can see down here is simulation successful. The output file is identical to the compare file. I'm having some trouble with my mouse radio. I'm gonna move it. I think that'll do it. Okay, that seems a little bit better. Okay. All right, what's next? And okay. All right, so I'm gonna say so here's my AND gate is just a knotted AND. That makes sense. A knotted NAND. Okay. So I'm going to do a NAND. A equals A, B equals B, out equals let's just call it in out. And then I'm going to say not in equals in out. And then I'm going to say out equals out. And then run. So what's happening in these test scripts? Load and.hdl, okay. Compare to and.compare. Output list AB out. Okay. Set A 0, set B 0, eval. Set A 0, set B 1, eval. Output. Okay. And then set A 1, set B 0, eval, output. Set A1, set B1, eval, output. Okay, that's cool. All right. Moving on. Whoa, what's happening? I'm gonna, oh, should I save it? I'll just reset it. Okay, whew. All right. The OR, here we go. Okay. So here I could just replace this with a Nand. But I'm just gonna follow. Oh, what is happening? I think maybe it's because I'm zoomed in too much. Huh. That's really big. Okay. Okay. All right, let's just, yeah. So I have a not, in equals A, out equals, what should I name it? N1 out. All right. N1, yeah. N1 out, not N equals B, that equals N1 out. Yeah, N2 out, okay. It's funny, because like when you draw something, you don't have to name the intermediate values. But when you write code, you do. All right. And maybe I'll just call it N1, N2. A equals N1, A equals N, B equals N2. Not N equals, I need the out. Out equals A out. Okay, it worked. I wasn't going to optimize this, but it seems like you could use like, I mean, you could definitely use a NAND gate here, right? I think that's the only thing I'd change, because then you're just using fundamentally like a NAND gate, a NAND gate, and a NAND gate. And I guess I'll go ahead and do that just for. So I'm gonna pump it into a NAND, and that'll be more efficient. And that would be equivalent to doing this. Yeah, this still works. So yeah, so like intuitively, like an OR has three, so from the enumeration of bits, OR is on, the output's on an awful lot. So in a NAND gate, most of the time, yeah, it has, yeah, the NAND gate has the three bottom ones Yeah. So it's sort of like you're just inverting it like twice to get the OR behavior. Okay. All right, let's move on. XOR. So it looks like, so basically I'm going to try going in reverse order and just say A equals no, I don't want to do that. I'm going to just go in order. Okay. A equals A, yeah, B equals B, and out equals and out. And then I'm going to do the OR. A equals A, B equals B, and out equals or out. I see. So it's sort of like we're using the Nand to mask the OR through the AND. Okay. So when I create the AND, it's integrating. So like the only difference between XOR and OR is this final combination yields a 0. So that's what that NAND is giving us, because the NAND is always true until you get to the last, the two true inputs, and then it's false. So we can use that to just combine it with the OR to mask out just that one. Okay. All right, now select. So Bitwig calls it select, and in the book they say like, oh, wouldn't it be nice if it was called select? So that's nice. All right, let's see. I really like this one. It's doing such a like cool thing, using a single output to carry two different signals. It's like an option. I mean, it's just cool that you can do that with logic gates. All right, so n equals, so I'm gonna start with a not, and I'm gonna say n equals the select bit, out equals, I'm just gonna call it not out, and just make it really clear. And then I'm gonna say and, so like we inverted that bit because when it's 0, we want to select the first input. We want to select A. So I'm going to say so yeah, I should name this not select, or maybe like select 0. And so if select 0 is true, so I'm going to say A equals select 0, and B equals my first input, which is A. Okay, it is what it is, and then I'm going to call this select 0 bit out, bit out, 0 bit 0. Yeah, I want to call that bit 0. So I'm going to say out equals bit 0. And then I need to say, so my select 1 is already true when select is 1. So like, if I want to select the second bank, this bank, I just have to say and A equals select, yeah, B equals B. So we're selecting from the second bank, which is called B in the inputs here. And then and then I'm going to say out equals bit 1. And then yeah, this is great. So there's an OR, and I'm going to say A equals bit 0, B equals bit 1, and out equals out. And that should be it. Okay, looks good. Now, why do I like that one? I think it's just because like it's just a few gates and it does something like that seems very intelligent. It's really cool. All right, so now we need a demux. Okay. All right, how does the demux work? It's very simple, isn't it? There's two outputs. So basically, we want to do the same thing. We want to say not in equals select, out equals select 0. And then this goes to an AND gate where the inputs are the in and the select 0, B equals select 0, and then my out is A. Okay. Yeah. So that's a little confusing just because of the convention. So the first letter in this calling convention, I guess you would call it, is the binding for that function, and the second letter is the binding from externally, from the code, from the broader scope. Yeah. The sort of the connections. Yeah. So like if we zoom in on our AND here, this would be A, this would be B, and this would be out. And then this would be in, no, this would be select 0, no. And okay, we're working with the top one. This would be A, this would be B, and this would be out. And then this would be, this line up here from not would be select 0. This line from the input would be in. And then this output is going to be A. So it's a little confusing because we have two things named A in the same function call, so to speak. Okay, so I'm going to do the same thing for the non-inverted input. I'm going to say A equals in, B equals select, out equals B. And that's it. That's really cool. And that works. Okay. And it looks like we have to do a bitwise not, which should be pretty simple. So is that how we in equals in, out equals, oh, I think we're 0 indexed, so I'll just do this. That's working. It's just very tedious, isn't it? All right, let's see. Oh yeah, I should, we don't need a llama. Okay, I'm gonna just do, I less than 15, no, 16, I plus plus. Oh, this isn't JavaScript. This is Python. For I in range 16, print, oops. It's probably easier to just open up VS Code and do this. I'm going to put F. How do you do it in Python? Okay, I should just use Node. Do I have Node? Yeah, okay. Okay. Yeah, I want to... Oh, come on. I don't know. Okay. All right, I think I can get this to work. Okay, there we go. Yeah, that's pretty tedious. Okay, I think that's it. Okay, that worked. Okay, so let's go to the next one, and 16. So basically I have two inputs, so it would look like A and A equals A 0 and B equals B 0. Out equals out 0. And well, I want to change that to like that. All right. And we'll just do the same thing. Except I need a console log. Okay. I forgot my semicolons. Oops. Okay. Okay, that one's easy. Or 16. Bitwise OR. Same deal. I think I can just do this. Oh, I forgot the semicolon again. All right, looks good. All right, mux 16. I think this one's pretty similar, except now we have a select. So I'm just gonna write console log. I'm gonna do a mux A equals A, and then I'm gonna template literal, so I'm gonna do dollar bracket I and square brace and B equals B of I square brace and then out. I want select. I want my select to equal select, and then out to equal out, and then I'll just copy this. Okay, and then I need a semicolon. I need close, parenthesis, semicolon, tick. Okay. Does that look good? Yeah, I think that's gonna work. Oops. And okay. So that works. All right, mux 16 or 8-way. So this one's a little more interesting. I drew it here. Yeah, it's just like cascading ores. So we need, looks like we need 4 ores. Yeah. Okay, A equals in 1. No, 0. And then B equals in 1. Out equals, I'm just gonna call it out 1. Yeah, that's fine. Or out. No, that was right. Okay, so it'll be out 0, I guess. So I want to say in 2 and in 3, and then out equals out 1, and then or A equals in 4, B equals in 5, out equals out 2. I think that works. Or A equals in 6, B equals in 7, and that is our out equals out 3. And that's good for our first layer right here. I'll just zoom in here. And so now I want the second layer, so I just need 2. A equals out 0, B equals out 1. And then I need to say out equals out 0, 2. Well, that's confusing. I'll just call it out 4. Yeah, I think I'd consider changing that to like second level or something, second layer. B equals out 3, out equals out 5. All right, and then our last layer, A equals out 4, B equals out 5, and out equals out. Okay, that worked. What's next? Mux 4. Okay. Mux 4-way 16. So a normal multiplexer is 2-way, So this is a 4-way, and it has 2 select bits, and I'm using constants as my inputs in this model. Okay. Excuse me. All right. So I'm going to say I want to start with I made the mux 16, so that's what I need. So I didn't demonstrate the mux 16. Well, unless you consider this as 16-bit input. It's looks like a float input, or whatever, it's untyped in Bitwig. So basically, yeah, I think I can just follow this. So A, B, C, D. So I'm going to say A equals A, B equals B. Excuse me. And then select equals, let's say select 0, the first bit. Well, let's double check. A, B, so is this select 0, or is this select 0? I guess we'll find out. So if we're wrong, there won't be much to change, but I think this is probably right. That's my guess. And if it's not, we'll test it. All right. And then out equals I'm going to call it out 0. That's good. And then I need another mux 16. And A is going to equal C, B is going to equal D, select is going to be the same as the first one, and my out is going to be out 1. Okay. Maybe I should call it out AB. This one could be out CD. Yeah. Or I could just say, it could just be like AB, like that. CD. And let's see, we need another mux 16, where A is going to equal AB, our B is going to equal CD, and our select is going to equal select 1, and our out will equal out. And if we got the bits right, it'll work. Okay, we got it right. We guessed right. That makes sense. I mean, yeah, it makes sense. I guess you think of an array going from left to right. And you think of a number going from right to left. I never considered that. Well, the most significant bit is going to be on the left. Okay. So here we go. So I made this next one and it's just 2. Okay, the next one, the mux 8 way 16 is just 2 of the 4-way 16s into just a regular 16, mux 16. So I just like reinvented the wheel here because I don't have a bigger select in Bitwig. Okay, but we don't have to. We can just use the work we just did to create this next one. So I'm gonna call our newly minted Muxway 16, and I'm gonna say we have like, you know, 4 inputs, so it'll just be A equals A, B equals B, C equals C, D equals D. Select equals. I don't know. I'm just gonna assume I can do this. I don't know. Maybe it's like a dot dot. Okay, yeah. And then so we're saying that the first 2 bits go to this part that we created before, which makes sense. And then our out will just equal I'll call it out 4 0. I'll just call it out 0. And then we're gonna do that again. And I'm gonna copy this, and I'm gonna say A equals E, B equals F, C equals G, and D equals H. And our select is still correct. And we're just going to change the name of the output to out1. And that's that's basically this section done. And now we just need another mux 16 where the A equals out 0, B equals out 1, select equals select 2, which is the last bit in that select, that 3-bit select, and then our out will equal out. And that's it. All right, it works. All right, we're almost done. And I know no one's watching, but I'm pretty convinced that the more you can visualize a thing, the better you can understand it. So even though no one's watching, I'm going to understand it better if I can see what's happening. And I'm looking at this next chapter, and I'm wondering how I'm going to visualize. I think we can keep going with Bitwig for a while, at least. But at some point, this is going to run out because the parts are just going to get too huge to visualize with without having submodules, and Bitwig does not have submodules. So, all right, demux 4-way. And it looks like that's what I have here. This this thing. So it's just okay. It's a mux, a demux. N equals n. Select equals. I'm gonna say select 0. Yeah, and then my out will equal, oh, what's going on? So my A will equal A, my B will equal B. No, I sort of need like an intermediate value. So I'll just say A equals out 0, B equals out 1. And then so that's the first fan out. And then for the second one, my in is going to be out 0. My select is going to equal select 1. And my A is going to equal A. My B is going to equal B. Yes. And then I'm just going to copy this and change this to out 1. The select is still correct. And I'm going to say C and D. And then that should be it. Simulation error. Okay. All right. Compare diff table. So what's going on? Okay, maybe it's just this. Maybe since we're going in reverse order from the multiplexor. Yeah, so that was it. So my select bit, since I sort of packaged it with the final select bit, I have to unpackage it with that final bit first before I can unpackage it with the first bit. Okay, that's nice. That was a nice way to learn that lesson. Okay. And the demux 8 way will just be sort of the same thing but bigger, and I have an advantage because I just made the demux 4 way. So for demux 4 way, excuse me, n equals n. So this is going to give me this fan out. And then I just need to fan out from each of these with a regular demux. Okay. No, I should use a regular demux. Because I should use a regular demux Yeah. And I want to address the last bit. So n equals n, select equals select 2, the last bit. And then my out will equal an intermediate. Wait. How does this one look? Okay, so we have two outputs. The first one's called A. So A equals out 0, B equals out 1. I think I'm going to change, I'm going to call it like an intermediate value. So I'll call it I0 and I1. Okay, so now I just need to put four-way n equals I0, the intermediate value, select equals select 0 dot dot 1 inclusive, and then it's a four-way, so I think A equals A, B equals B, C equals C, and D equals D for this one. And then, yeah, then I'll copy paste this, and I'll say intermediate value 1 for the n to the second one. The select is still in the right range, but this is going to be A equals E, B equals F, C equals G, and D equals H. Yeah. And that should work. It worked. Okay. So I think doing it in that order was really effective because I think it's easier to think about how the multiplexer works. But yeah, than to think about how the demultiplexor works. So that's really cool. I think there's a lot of similarities when you get into like the one that's like the integrating or the integrating and then there's like an integrating multiplexor and a disintegrating demultiplexor. Okay, so this is really fun for me. I know nobody's watching, but I'm having fun. And you know what? It's been like almost an hour on this live stream, and we finished up chapter 1 of the Elements of Computing Systems. And I am excited to get to chapter 2, where we're going to build an arithmetic logic unit. So, to all you imaginary people, stay tuned. We're going to have more fun. All right. Peace out.